Welcome back to the Verilog lecture series class. So we have seen the Verilog model of the D latch. The next one we will write is the D flip-flop, and before that there are a bunch of slides that sort of recall the generation of the clock and writing the test bench for the that we have already used in the D latch. We'll just go through these principles again. So you already recognize the initial block, which is encapsulated within a beginning and end. So this initial block is only creating the clock, and it is repeating the clock edge for say 30 clock cycles, and the rough output is also sort of shown over here. The initial block, as you already know, starts when the simulation begins and does not end until explicitly we have mentioned the finish, or it doesn't end until all of these statements have been fully executed, right? And so this initial block, the first thing that the initial block does is for this signal called clock, which could be declared outside this block, inside the module block, right? So this clock is already declared and it is now initialized to 0 at the beginning of the simulation, and what happens after that is wait for 10 time units, and then clock is basically complemented. That signal is complemented, and the cycle of complement happens for 30 times. So that is of every 10 time units, the clock signal goes from high to low and low to high, thereby simulating the clock signal, right? You also know that the initial block executes exactly once, and any number of initial blocks can exist inside a module in the test bench. Any number of initial blocks can also coexist with any number of always blocks inside the test bench. This is basically the description of the clock signal. It's a single bit value that oscillates between 0 and 1, and this block is repeated 30 times. So you already know that what the meaning of the hash and a number next to the hash is. Hash is what is called as a delay control operator, and a delay control operator instructs the Verilog simulator or the Verilog runtime to stop execution or to suspend execution until this time elapses. So as soon as this delay control operator is encountered, so the Verilog runtime will wait for 10 time units to elapse before executing this instruction. Then sort of again loops back, and in the next iteration again waits 10 time units to execute that instruction again. This of course you already know that tilde is a negative signal, and this is actually a comment. Right, so this is how test benches are written. You've already seen this in the case of the D latch test bench, right? You could do the finish in a separate initial block, or you could write the finish right after this, at the end of this initial block, thereby giving independent handle on when you want to finish your simulation. The another way of writing the clock or generating the clock is also like this. At the beginning of the simulation, we initialize clock to a meaningful value of 0, and there is an infinite always loop that has just one instruction, a delay operator, and then clock is negated every 10 time units. This is also another way of generating the clock. This initial block has only one statement, so there is no begin and end. So what this basically says is finish the simulation after 300 time units. So you already know what the always block does. It executes infinitely repeatedly, and in this always blocks we don't have an event sensitivity list, so it's like an infinite loop that is always running in the simulation. And also this always block has only one statement, and that is to generate the clock. So all of these always and initial blocks, they execute concurrently. They are all active at the same time inside a module, once the module is instantiated and the simulation is being run, these blocks are executing concurrently. And it doesn't matter in what order you write these blocks inside the test bench. They will all be, because they're all equivalent to hardware, they're all equivalent to placing a hardware chip on the breadboard, and it doesn't matter which chip you place on the breadboard first. Once you turn on the simulation or once you turn on the power, all of them are active at the same time. So the same principle applies here also. Initial block number 1, 2 and the always block number 1 here, they can be written in any order. The final functional effect will be identical. The next operator after the delay control operator is the event control operator, and we have met the event control operator already in the first statement of the as a part of the always block. For example, even the latch behavior we had mentioned always at the data input D to mean that execute these bunch of statements inside the always block when D changes, right? So what actually happens in the simulation is that this always block activity or this always block by definition has to be executed repeatedly, right? Once the event control operator has been put in, the meaning changes to suspend activity until this event occurs, and the event being is the modification, or if the signals that are mentioned inside the parenthesis after the event control operator, when one of them change or one of them is modified, that's when the event is said to have occurred. Until such an event occurs, suspend activity or do not execute this always block. That is the meaning of this event control operator. You have to contrast this with the delay control operator. What the delay control operator says is until these many time units expire or these many time units are elapsed, do not execute or suspend activity until these many time units expire. So that is a time bound event, and the event is said to have occurred after the time has been elapsed. Whereas with the event control operator, the event is said to have occurred when one of the signals inside this list of signals has been changed, whose value has changed, right? So any change in the signal A will trigger the next bunch of the next instruction after the event control operator. And for a sequential circuit, we've already seen it in the latch, and in the case of the flip-flop, we know that the event of interest for us is the rising edge of the clock, right? So for a flip-flop, for example, the always block will get triggered or should get triggered at the rising edge of the clock, and the way we express that in Verilog is the event is called passage of this signal called the clock, right? So this basically means this event is said to have occurred. The rising edge of the clock is said to have occurred, right? And we encapsulate this event control expression inside the always as the statement as the always block trigger, and so and this will be the expression for the flip flop, right? So the other rule, again we have already met this rule. Any assignment inside the always block, the LHS has to be of type reg, and that's why for the DLatch also we had declared the output was by default Q. However, we had put an extra additional statement that Q is also declared as reg type. The list of signals that we write over here inside the parenthesis, the list of events or the list of signals that we are interested in is called the sensitivity list. An example of the sensitivity list is shown over here. So basically the event is a modification in any of the three mentioned signals A, B and C form the sensitivity list. If any of these signals change their value, then the successive statements, so that's the trigger, and the successive statements will be executed. We are interested in the rising edge of the clock for the flip-flop, right? And this could be the always block inside the flip-flop. So Q and a non-blocking operator and the input data. So what this block indicates is as soon as the clock rising edge occurs, so this is the event and this is the event for this is the clock. And at the rising edge, Q gets the value of D. So this is the first time you are looking at this non-blocking assignment operator. Till now we have always used assign Q equals D. So let me explain the difference between the equal sign and the non-blocking assignment statements. So when included inside the always block, both of these statements differ from each other such that this is sequentially executed. The one on the left, this is the sequential, or the execution is sequential. It's not the sequential in terms of the digital systems. The execution of these instructions are one after another, right? So that is the sequential execution, very similar to the C programming or any programming language that you already know, right? So the final effect of this set of assignments will be that the signal C will be equal to A plus 1. If you had to sort of map this to hardware, what it would look like is A, so the signal B gets the value of A, and there is some sort of processing that does B plus 1, and what is coming out of it is C. So this is sequential in some sense. That is, the input signal A is sent and becomes B, and then B gets modified for some computation, and then the output C is generated. So this is in some sense sequential. In the case of the non-blocking assignment operator, right, both these statements, both the statement number 1 and 2 are executed simultaneously. So thereby the final value of C will actually be B plus 1 and not A plus 1, and A gets assigned to B at the same time simultaneously as B plus 1 will get assigned to C. So let me give you a sequential logic example to illustrate this. So let us say you had an always block, and we'll write say pos edge of clock, and now we want to differentiate between the blocking and the non-blocking. So first we are familiar with the blocking, so I'll just write out the blocking statement. Say you have two statements, B equals A and C equals D, and now we understand that line number 1 and line number 2 will execute one after another. So the meaning here actually becomes like this. There is an assignment from A to B, and what is assigned from B is actually assigned to C. So finally the value will be equal to actually C. C will get the value for A, and all of this happens at the pos edge of the clock. So at the pos edge of the clock, anything that comes in the begin and the end statements actually will get modeled, or right now we are modeling a flop, actually a flip-flop. So at the pos edge of the clock, so we have one input, and that input is A, and two inputs B and C. In fact, both of the inputs B and C will have the same value A at the end of this modeling, at the end of this model, right? This is what we have modeled here. This is for the blocking statement, right? So this is what happens when we have used the blocking statements. So let's see what the equivalent is for non-blocking statements. So again, we are considering the same block, always block, and we'll look at the behavior at the pos edge of the clock, and we have the begin and end, and instead of the previous blocking, we are now writing the non-blocking statements. Assigns to B. And what is now happening? This line 1 and 2 are executed simultaneously. So because they are executed simultaneously, they are two independent assignments. They are not dependent like the previous blocking set of statements. These two statements are not dependent on each other. So because they are two independent statements, we should so the model that we have now described is actually two different flops. The second flop, the first flop is basically same as the previous one. It takes an input and gives an output of B, and the second flop is actually takes an input of B and gives out the output as C. However, we also have the B output available at this point. So this is B and C. So this will be the this is the description. Of course, this is the clock then. So I hope this example illustrates the difference between blocking and non-blocking statements. And non-blocking statements are used in the description of sequential logic. And so when we are writing latches and flip-flops, actually non-blocking statements is what we have to use. Right, so this is what we have gone through. So statements execute sequentially in the case of blocking, and assignments are done concurrently in the case of the non-blocking. Blocking statements are used when modeling combinational logic, and non-blocking statements have to be used when we are modeling any sequential logic, including latches, flip-flops, or any other edge-sensitive behavior is to be described. Non-blocking assignments have to be used. So in the previous latch example, I had used the blocking statement. However, this is the correct form of writing the Q follows D equation in the latch. This is the Verilog model for the D latch. As you can notice, there are a couple of small differences from what we had written in the previous class. Always and the sensitivity list here contains two signals. One is the enabled and other one is the D when D changes. So and the other major change is the blocking, the use of the non-blocking statement. So this is the alternative way of modeling the D latch, and the more accurate way of using the non-blocking operation to model the Q behavior. Next, let us look at the model of the flip-flop. For the flip-flop, the sensitivity list includes only the passage of the clock. That is to effectively say, any practical work that is done by the flip-flop is at the positive edge of the clock, and when the positive edge happens, the value at D, right, the stable value of at D should be assigned to Q. So whatever Q is, just after the rising into the flop, it will just copy the value of D to Q, and that is what has been described in this one line inside the always block here. So that is the description of the flip-flop. We can use the same test bench that we had already written for the latch, or maybe you could write a new one, but I think that is already enough for testing this flip-flop. So I'll model the original D latch that we had written in the previous class for the D flip-flop. So here, and we'll call this with the correct name, right? Clock. So input is this Q. Right. Sensitivity list contains passage of the clock, and do it always passage the clock happens, and this is it. This is it for the D flip-flop. Let me do the D latch. The D latch TB is already usable for the D flip-flop. Let me just make the minor changes that are required. And, okay. Just write correctly. So we are instantiating the D flip-flop. Say D dff1 generate the clock. So wherever there's an n, let me just clock like clock 0 power, this is the clock, stimulus is this, and we had already a bunch of D behavior here in the monitor. Yeah, let me check if the monitor pass and fail is correct. So if q is not equal to t, then fail, that's right. So let's see if this works. So we have so when q equals 1, t equals 1. So that's it. Yeah, so there is nothing surprising about that result. So that's the implementation.